who is Livni, and he's going to talk to us about algorithms and learning. And I'm sure that more people are going to be coming in just as soon as they are able to empty their plates.
You want me to start or wait?
I think, they're going to miss the little bit of introduction, and they're going to stay out there until they say,
Yeah.
Maybe I should go outside and say I'm offended by okay, you don't want to come to me.
I think we should start.
I was here when you talked. But like I liked your talks. Okay, so this is work about trying to understand what makes algorithm learn. It's a joint work with a lot of people. Most important, I'll introduce the students. So it's Idan Amir and Asaf Dauber, which was my MSc student. Idan Amir is finishing his PhD, and Uri Sherman, who is a PhD of Tomer Cohen. So I think everybody knows this picture of learning and hardness. You have a task, you get to see samples. The samples, you want to find, the samples are labeled, and you want to find, let's say, a half space that best classifies them. So the task is agnostic, meaning there is no optimal classifiers, and this is known as a hard task. You can relax it a little bit, and you can do what is called improper learning. You will learn a model which is a little bit less stringent. Doesn't have to be half space, but does have to be as good as the best half space in the class. That is still hard, not anti-hard, but still there are cryptographic assumption or average case assumption implicit, so it's hard. But for machine learners, there is also another extreme that you can do, which is called interpolation. Okay, what does it mean to do interpolation? You take the data and you find some model that completely fits your data. Okay, and that is not hard. Okay, it's very easy. One thing you can do is nearest neighbor. You can memorize. You can do a lot of things. Only it still doesn't make sense because it is statistically hard, right? Most of the chances are that if you're just going to interpolate your data, nothing non-trivial is going to come out of it, right? This is called overfitting. So why should we care about it? Because when you look at common practice today in machine learning, it seems as if most of what's going on today in learning is happening in this regime. Okay, so what is done today when you train what is called a neural network, basically you train what is called an underdetermined system. There are more free parameters than examples, which kind of makes the fact that it fits the data seems at least not surprising. I mean, it's a nonlinear system, so the fact that it interpolates is not trivial, but there are certain proofs, like you can prove for certain systems that yes, they will interpolate. Of course, you're not going to go every architecture out there in the market and start proving, but you could do the following experiment. You take a neural network, you take a training algorithm, and you run random data. Okay, you check what's going to happen if I give it random labels. And what's going to happen is that it is going to interpolate random labels. And there was many discussions here about how basically if you interpolate random data, then you can treat it as if it interpolates anything, right? Because if it doesn't interpolate something, then something non-trivial happens, right? You got the separation from random data. So as far as we are concerned, we can basically treat these algorithms as algorithms which are interpolating random data. So at the end of the training process, you trained an algorithm over some data, nothing really surprising happened, okay? And yet, you take this output and you check it on test data, something that it had never seen before, and you see that something non-trivial did happen. It generalizes outside of the data, okay? And you want to understand this. You want to understand what happened here. You can think of it as if basically I look for a circuit, but the circuit is complex. It's allowed to be as complex as the data which it needs to fit, and yet somehow inside something is going on, and the circuit is non-complex in some sense, but you don't know in what. I want to understand this. Now why the PAC model doesn't feel like really a convenient model to study such a phenomena. So I think you know the PAC model. I'll just skim over it. I'll call it the MAC model and not the PAC model because it's a model that is a little bit easier to introduce. It's not probably approximately correct. It's mean approximately correct. It's a completely equivalent model, only one quantifier less, so much simpler for slides. What do you have? You have annotated data, x, y's. They are generated from some unknown distribution. The algorithm gets to observe samples, and it returns a predictor. And what does it mean to learn a class? Where with sample complexity m epsilon means that if you saw m epsilon examples, then the expected error, so expectation here is over the sample, the expected error is as good as the best classifier in the class plus maybe epsilon. Okay, so this is the PAC model, and we know a lot about it.
Explain what's the difference between PAC and MAC.
So in the PAC model, you would have m epsilon of delta, and you would require that with probability 1 minus delta instead of in expectation over the sample. Okay, but with Markov inequality, you can move from one to the other. And if you want log 1 over delta, it's equivalent. Okay, and we know quite a lot about this model. And this is known as the fundamental theorem of learning. And it all boils down to the following. The following are equivalent. A class is learnable by some algorithm, meaning there is an algorithm that learns. Forget efficiency aside. If the class has what is called finite VC dimension, we won't go into that, what it is, but it's some combinatorial property. And then you also know what is the sample complexity. The sample complexity is the VC dimension divided by epsilon square. And you also know how to do it. Like I can tell you the algorithm. As long as you put efficiency aside, what you should do if you want to learn is basically, it is called empirical risk minimization. It means take your data and find a model in this class H that best fits the data. That's all you should do. That would work. Okay. And the problem with that for our purposes is that basically this theorem says you should not do underdetermined system. You should not do overfitting. You should work in a regime where the VC dimension, which kind of captures the number of parameters in your model, should be less than the number of examples. And really, the algorithm doesn't matter. It's not about the algorithm. It's about how many samples you have and whether you fitted or did not fit the data, which is obviously not the case in interpolating algorithm. Interpolation means that the algorithm very much matters. Obviously, if you're going to do nearest neighbor or just memorize your data, that's not going to work. So it's really not clear how are you going to study these models that are interpolating in this setup, which kind of says, don't do it. So how is it resolved? Like how are we expecting? So basically the idea is to treat what is called non-uniform rates. And the picture that we have in mind is you kind of think of it like this. You have an algorithm A that observes the data and output something, the predictor. And yes, it will interpolate the data. But from all of the solutions that interpolate the data, it's probably going to choose something simple. Well, what is simple? I don't know. And then you can kind of use like the uniform convergence bound or the simplicity. So if there is a simple solution, somehow from all the interpolating solution, my algorithm kind of found this simple solution, and this is what it did, right? And then I can prove generalization. And now I'm left with the question, but what is simple? Like I have neural networks and they find something very complex, but something in it is simple, but I don't know what is it. So you can think of this as a meta complexity question. Like something is finding a circuit, this circuit is simple, but I don't know in what sense it's simple. And I would like to find out. I would like to look at the system, check it, find something in it that would tell me, aha, the system is trying to simplify the solution by doing X, Y, Z. Okay, so let's start with an example. And this example will also be a good place to introduce stochastic gradient descent, which we will talk about. So here's a very, very simple problem. You have Z, which are -1, 1. It's scalars, everything low dimension. And what you want to minimize, W dot Z. Okay, so we want to find a scalar which is anti-correlated with Z. Okay, and you can assume you want to find it W in a bounded set, like between -1 and 1, or -infinity and infinity. Doesn't really matter. And it is an algorithm. Okay, there are a lot of ways to solve it. I'm not saying this is the only way to solve it, but here is an algorithm which does the following. It is given a sample, and it works iteratively. And at each iteration, it starts at state 0, and then it moves against a new example. So it draws a new example. If it's positive, it moves negative. If it's negative, it moves positive with some steps. Okay. And this is how this algorithm is searching for something that will be anti-correlated with the sets.
Sorry, this is a one-dimensional layer, so the dot product is just times.
Yeah, sure. Times. And okay, so it's an algorithm. What does it simplify? What types of solution does it find? So it really just derives this and equate to 0. You can see that what this algorithm really do, it basically converges to the solution of the following equation, which says minimize your empirical loss minus your empirical loss plus an additive term, which is to penalize the absolute value. Here it's also absolute value, not anything else, but penalize the norm of your W. So it kind of looks for a solution that is anti-correlated, but also is regularized. Like it is simple in the sense that the solution will be kind of close to 0 as much as possible. And this is sometimes referred to as implicit regularization. Okay? So you can think of implicit regularization as something in the algorithm that makes it choose a simple solution, even though explicitly it did not appear in the requirements of the algorithm. Okay? I did not put it in the objective that it minimized, but the way I minimize the problem led me to a solution which is simple. Here in the sense of how far the number is from 0. Okay, so questions over? Okay, so this is a case where we kind of.
I think there was a question.
Yeah, well, I'm just trying to see where the regularization is happening. If you want to minimize that quantity, you would just set W to be infinity or negative infinity.
Yeah, I'm saying you can solve this problem. So you won't want to choose -infinity or -infinity because you have finite data.
No, you would look at to minimize the expectation over Z of W.
Yeah, I didn't say what this algorithm like solves.
Oh.
I just said this is an algorithm. Like if I would, there are other ways to solve this algorithm. If I would bound this, then you would not necessarily use stochastic gradient descent. But as a learning algorithm, it is a learning algorithm. It searched for a solution for this problem, and it searched for the solution that is regularized. Do you need regularization here?
Converge to negative infinity? Sorry, missing something? I think there might be something missing, or no?
So yeah, so I said you can assume that you look for in a bounded set. Okay. W are constrained, but it doesn't matter because I'm not saying that this is the right algorithm for this problem. I'm just saying it finds this solution, the regularized solution. Okay, this is a very simple problem. You don't need regularization. There are other things you can do. But here is an algorithm. I try to find out what this algorithm. I'm not thinking about solving the problem. I'm thinking about studying the algorithm. Like, what does this algorithm do?
I just think there might be a mistake in the equation. That's just adding up eta times all the numbers.
Sorry?
Anyway, go on, yeah.
Okay. Okay, so now we want to do this in other setups, more complicated setups. And we kind of said, okay, let's take stochastic convex optimization, which I'll introduce in a minute, as some sort of a case study. Okay, a setup where we want to understand what algorithms are working, why are they working, what is it doing. And there are various reasons to choose it. First, it's a very simple setup. There are no hardness results. You have algorithms that you can show that they are provably generalizing. And these algorithms are also prototypical. They are gradient descent, stochastic gradient descent algorithms that are actually being used in practice. So it's like a good place to start. And also, I think most people would say that, and I'm not saying it's true or not, that it's like the simplest thing you can think of before going to complex systems that are non-convex. Like you have linear systems, then you have convex systems, and then you have things like neural networks. So seems like a good start. Like if I can understand things in convex optimization, I might hope to develop tools where I will understand them in more complex setups. Okay, so what is convex optimization? So the setup is very similar. You have data that is generated from some unknown distribution. We're going to look at the case where the class we are minimizing over is a unit ball in RD. So we have a loss function, FWZ, which is Lipschitz and convex in W for every Z. And then you have an algorithm. The algorithm observes S, the data, Z1 to Zm, and it returns some predictor or solution. Okay, what is an algorithm? I'll need to define, but for now, let's think of an algorithm as an abstract object. Okay, just a mapping that takes samples into parameters. And again, the sample complexity is M epsilon. If for large enough sample, the expected loss of my function is as close to the minimum as epsilon. Okay, so in prediction, basically F is just a 0-1 function, which is non-convex, so it's not part of our setting, but you can look at the setting where F is convex. And what is the second thing that is very interesting in the setup is what I like to call the anti-fundamental theorem of learning of FCO. This is a result from 2009 by Shalev Schwartz, Shamir, Sribro, and Sridrahan, where basically they showed that the fundamental theorem is not true in this setup. So what does it mean it's not true? So if you look at ERMs, empirical risk minimizers, so you just look for the solution that minimizes the empirical loss, then we know that if you saw D over epsilon squared, D is the dimension, then that's enough, that would work. Same tools as VC theory, like uniform convergence and all of that. And also it seems to be necessary. So what exactly do we know? So Shalev, Shamir, Sribro, and Sridrahan, they showed that you need at least log D examples. So the number of examples you need for ERM to work is at least dimension dependent. And then Feldman improved it to show D. But still there is a gap, right? You see, so we don't know if it's D plus 1 over epsilon square or D over epsilon square. But what's important for us is that it's dimension dependent. Okay, ERM is dimension dependent. The dimension is a real factor in the problem. But you can do better. Okay, if you run the right algorithm, you can achieve sample complexity, which is 1 over epsilon square. And in this case, regularization is exactly what you want to do. You want to minimize not the ERM problem, but you want to minimize the regularized ERM. Okay. And I think this theorem is kind of, I think, mind-boggling, because if you think about it, what it says is kind of something like the following. Let's say I have a student and I want to check if this student knows the answers to my question. So I randomly pick up questions, and let's say 10 questions are enough. I have a certain amount of accuracy, a certain amount of confidence, and 10 questions are enough to check him. But then I check millions of students, right? And these millions, I know that some of them if I give them only 10 questions, they are going to randomly guess the answers. So at the end of the test, I get these answers to the test. A lot of students just randomly guessed. Okay, the empirical risk minimizer will not work because there are solutions that are just overfitting. But somehow I have this method that from all of these students, where some of them answered correctly by guessing, and some of them answered correctly because they know, I somehow find the right ones. Okay. And I'm not saying there is a way to do it. There isn't a way to do it. Okay. It would be very racist of me to say that there is. But in convex optimization, there is. Okay. And it's kind of weird, but it's true. So let me show you why ERM fails. So the construction is, I'm going to show you the construction of log D, not D, because it's much simpler. So the idea is like this. So my Z's are going to be 0, 1, where each coordinate is 0 with probability half and 1 with probability half. And my loss function is going to be Wn squared times Zn. So if you look at the expected loss, it's basically half the norm, right? Because each coordinate with probability half, I'm paying W squared, and with probability half. So that's my true loss. But when I look at the sample, and if the sample, if I have D, which is larger than 2 to the m, m is my sample, there is going to be one coordinate, which is 0 on all my samples. And then what an ERM might do, it might choose this standard basis vector. And as far as the empirical sample tells you, there is nothing wrong with it because these Zns are 0. So you're allowed to go there. So this shows that an ERM makes it. And then you need to prove that regularized ERMs will succeed. I won't go into this proof, but it relies on a notion that is called stability, which basically means that if I change the sample a little bit, the output of the sample doesn't change a little bit. And you can prove that stable algorithms do not overfit. So once an algorithm is stable, it doesn't overfit. And this is how the proof goes. Okay. So let's go deeper into stochastic convex optimization. Now I want to talk about algorithms. So now I need to define what is an algorithm, because I said it receives functions. What can it do? So for this, we're going to define the algorithmic assumption, which means that I have what is known as a first order oracle. That means that I can ask from the oracle for every point and every zi's, I can ask for the gradient of the function, and I can ask for the value. I'm not going to use this. I can ask for the gradient of the function. Okay. So that's my algorithmic assumption. So once I have this, all the operations I want to do over the vectors, I can do. I can add them, I can subtract them, I can do whatever I want. But as far as the function is concerned, which is this abstract notion, this is my algorithmic interaction with it. Okay. Okay. So let's take an algorithm now and start studying, start understanding how it generalizes or doesn't generalize in this setup where the algorithm really matters. So we start with gradient descent, which is probably the most naive algorithm you can think of in this setup. What does it do? At each iteration, it computes, it goes to WT, so it starts at W0. It moves from WT to WT plus 1, where WT plus 1 is WT minus the average gradient over the sample. So this is the empirical gradient at that point. Okay? And then, okay, so you need to do projections because you care about eternal sum for a unit ball, but you can forget about it. Everything we're going to do will not require projection. And there's also this thing that you need to take the average output. And again, like in all the construction I will show, you don't actually need to do that. But there are, like, if you want the algorithm to be principled and have provable guarantees, then you would need to do that, or at least optimal provable guarantee. Okay, so this is an algorithm. What can you say about it? So the first thing, so this is a very classical result and very well known, which says how does it behave with respect to the empirical loss? Because it minimizes the empirical loss. And you can show that basically if you choose the right parameters, then you will get error of 1 over square root n. You don't want to get anything less than that because that's your statistical error. So choosing your parameters in a way where you get error 1 over square root n makes a lot of sense. But actually, we did not know if it's even a generalizing algorithm. And we checked this, and it turns out that no, the algorithm will not generalize if you apply it like this. It turns out that in the generalization error, there's going to be, instead of eta square root, which kind of means that if you choose your parameters in the same way that you choose to minimize the empirical loss, you will overfit. You will get omega 1 error. You need to choose your parameters a little bit more careful, which means that you need to take m square steps and not m, and then it will generalize. And this is also time, okay? Because Basili, Feldman, Guzman, and Tawar, what they showed is that this also bounds the stability of the algorithm. So in other words, if you choose your parameters this way, the algorithm will generalize. If you choose the algorithm this way, the algorithm will overfit. So this is a great situation. You actually have an algorithm, it doesn't generalize, you have a fix, and we can study what did this fix do? How did this fix add some regularization or some simplicity to the solution, which made it succeed, right? So that's what we try to do. And well, first, before that, we got the following result, which kind of says that if you're going to look for some implicit regularization in this algorithm, whatever steps you choose, that's not going to work very well. Because there are convex functions where, so in this convex function, the set of minimizers, all these lines, so these are simulations, but we proved it, okay? So these are provable results. And you can make gradient descent go not to the closest minimal norm solution. But on the other hand, you can also make it go to the minimal norm solution. So you could have two problems when one of them, it prefers this solution, and other, it prefers this solution. Which in other words, means that you cannot think of it as something that minimizes empirical risk plus some other term. Okay, it doesn't do a Pareto optimal solutions, because for any, you can extend it to any function where you give me a regularizer and say, okay, gradient descent tries to simplify the problem by minimizing R. And I can show you, okay, so I'll construct a problem where there is two solutions, one of them R prefers, but gradient descent will go to the other, even though empirically they are both completely equivalent. So in other words, I cannot think really about gradient descent as some implicitly regularized algorithm. And this has nothing to do with the number of step size, right? It's true for if I run it like this, or it's true if I run it like this. Also, like we said, okay, so one way to solve it is by changing the step size. What about regularization? So we saw regularized ERM failed, but regularized ERM succeed. But it turns out that if you want an algorithmic analog for this result, so first it didn't work. What does it mean it didn't work? We took algorithm over the regularized objective, and this is a little bit subtle because when you run optimization algorithm over strongly convex, you need to kind of change the parameters if you want to enjoy it. But we took the algorithms that we knew existed for this problem, and in all of them, like it always showed up somehow, this m squared. Like if we choose some parameters, then the empirical error would behave like this. This is the known classical bound for gradient descent over a strongly convex function. But then like this quantity appeared here, which again meant that we need to take m squared steps. So what was solved by changing the step size was not solved by regularization. Regularization actually did not even achieve what could be achieved otherwise. And this was quite general. What does it mean in general? We kind of showed that it doesn't matter really what the algorithm do. As long as it relies on an oracle that returns the empirical gradients, with gradient descent. Gradient descent is noise. Gradient descent plus any type of regularization you might think of. Any algorithm like that would need m squared steps. Okay? Which means basically just run the algorithm without anything. Don't add regularization, don't add noise, it doesn't matter. There's nothing structural that you will add or benefit by adding something that regularizes the solution. I'll go a little bit about the proof idea. So again, the first ingredient, we need to make sure that ERM will fail. So we take Shalev-Schwarz construction, and then we have this max function, which basically says max over the coordinates. And what's nice about this function is that the gradient looks like this. So it takes the coordinate where you are most maximized, and this locally you look like this function, like this coordinate. So the gradient is always the coordinate that is maximized. And then what you want to do is you want to start with some, what you want to do is you want to make like the ERM that we saw before that maximizes those coordinates where this is 0. And you use this max function and some perturbation, which is correlated with the Z. So that would mean that you first perturb the solution to a little bit amplify those coordinates that are 0 over here. And then the dynamic will be that this algorithm will start pulling them down. And because it's not an exact algorithm, it will pull them down too much. And eventually you will get a solution that is very far from 0 and doesn't minimize. Okay, so that was our story with gradient descent. Then we move to stochastic gradient descent. So what is stochastic gradient descent? Stochastic gradient descent is a very similar algorithm, but it does something much smarter. Instead of each iteration to take the whole empirical risk, it just samples one point and moves in that direction. So it seems like a much lighter algorithm. You probably are going to pay for not looking at the whole gradient because it's much more noisy. But it turns out that no, you do not pay at all. It's a much faster algorithm because you don't need to compute all the gradients, and it has the same guarantees. And not only it has the same guarantees, it has the same guarantees with respect to the true risk, which kind of means that this algorithm, you don't even need to correct it. It is with m steps. We give you 1 over squared. So it's much better algorithm than gradient descent. Not only it's lighter, but in fact it enjoys generalization properties that gradient descent doesn't have. And I want to go over the proof because the proof is very interesting and very simple. So the proof is like, and this is the proof by the way of gradient descent. So I'm going to ignore projections, but the proof is like this. So you look at the solution at step t plus 1. So we just the Newton binomials, it's wt minus w star plus what you added, the gradient, plus the gradient. So which kind of gives you a bound over the first order approximation of your function. You take this term and move it to the other place, and you take this term and move it here, and you get this bound. Okay, very simple so far. Don't expect you to remember it, but there's nothing really to be done here. It's like the thing that you would normally do. And then you look at the true risk, and you first use convexity, the fact that WS is the average point. And then you use convexity again, where you say, okay, this is bounded by the first order approximation of the function. This is convexity. And now comes the only non-trivial step, which says that the expected value of the scalar product between the gradient and Wt minus W star, because Zt is independent of Wt, Zt is a new example, then the expectation of these two is the same, which means that I can replace these terms with these terms in expectation. And then I take this inequality and I plug it in and I divide by eta. And now I have something that telescopes, and this I get rid of, and this is it. This is the proof. Okay. Why did I show you the proof? So the reason I showed you this proof is because there is something very, very unique about this proof. Okay. What I did not do in this proof, I never showed you that the generalization error of the algorithm is small. I didn't show that it is stable. I didn't use uniform convergence. I didn't do any of those things. And almost all other proofs, like any other proof that you prove that something generalizes, the proof starts with this bound, that the test error is bounded by the training error and the generalization gap, or generalization error, depends on what you call generalization error. And this you prove by optimization. So you show I have an algorithm, the algorithm searches for the best solution over the data, and you prove something. And this is usually what is being controlled by all these complexity measures that measure simplicity of the solution. The VC dimension, stability, you can use privacy, compression, all of these things that says that the solution is very, very simple, therefore it will generalize. It goes here, it doesn't go here. It goes over the generalization error. And this is where regularization takes effect. If you just care about this, you would interpolate and you will not care about this. But because you care about this, you do more, you add regularization. But the proof didn't do it, right? I never showed you that this is small, and I never showed you that this is small. So how am I going to show you that stochastic gradient descent is regularized where I never even showed you that this is small? And it turns out that I didn't show it to you for a reason. This doesn't happen small. So what we can show is that basically SGD never minimizes the empirical risk. You could generate learning problems where you run SGD, it learns. It will minimize the true risk. You'll get a good solution. But if you look at the empirical risk is very, very large. So we don't show it's. So the equation here is the right direction. Yeah, this is the right direction, but it's not exactly that we show that WS overfits the loss, it underfits. It gives you something very pessimistic over the sample. And this is something that cannot happen if WS was simple in any sense. If you could bound the complexity of the output of the solution, then you would have a generalization error gap. You have a bound on the generalization gap. So you don't have that, which means that stochastic gradient descent is outputting things that are inherently complex. It's not like I cannot find what is simple about it. It is actually not a simple solution, which would kind of be okay if it weren't stochastic gradient descent, because it's not that difficult to generate pathological examples where something like this happens. But the fact that SGD, which is, I think it's like the backbone of every algorithm, like it makes no sense to come up with a theory of learning that says, but SGD is a pathological algorithm. To think of SGD as a pathological algorithm, that's a problem. Convex optimization maybe, but SGD no. So questions or? Okay, so a little bit about the proof idea. So it relies on a very similar idea where you kind of use the same construction again. Only this time, we're going to make sure that the ZNs are 0 almost always. But some of the coordinates are going to be 1. So there are going to be coordinates where it looks like you shouldn't choose something that is large there, but actually in reality on the real data, it doesn't really matter. And then again, we want to correlate this noise and make sure that we increase those coordinates. So there is some challenge because in stochastic gradient descent, you can only depend on the last coordinate, but what you can do is you basically can encode inside your last state all of the past coordinates, and then you can somehow find what are the coordinates that until now are mistreated, like the z ends are 1, and then you make the dynamic simply go to those solutions. So some further result is that we can also show that SGD with replacement will generalize. But again, you don't get a proof that builds on complexity. It doesn't say anything about that the solution is simple or non-simple. It kind of builds on this twisted argument where it says the regularized theorem cannot overfit, so this solution cannot. And again, like, why would that algorithm work? What makes the solution regularized in some sense? There are also certain structural properties of gradient descent that do, under certain situation, mean generalization. Like you can show that it is not implicitly regularized. There's no regularization that is distribution independent, but for every distribution, the solution is going to be somewhere in the proximity of a solution that depends on the distribution. But this is not enough to prove generalization. So it is an implicit regularization of the algorithm, but nothing that can be used to actually prove generalization. And that's it. That's what I want to tell you.
Do you have time for questions? In that case, let's thank him again. We'll begin at 11:30. See here when the bell goes.